What's poppin', dogs? It's Mr. Allen with some trigonometric ratios. We got to find all 6 trig ratios for each one of these examples here. And I don't have all 3 sides of this triangle, so we got to hit this thing with some Pythag. If you remember your triples, this is an 8, 15, 17 Pythagorean triple. Boom. Or you could just, do 8 squared plus something squared equals 17 squared and do a whole lot of work, but it's a triple. All right. So now I'm looking at, from theta here, from this angle right here, I got to get my sine ratio. I'm not looking for the angle. I'm just looking for the ratio, the fraction. The opposite side will be this guy right here. The adjacent is the 15, and this is my hypotenuse, right? Helpful to lay that all out because we're going to be doing this 6 times over. So opposite side is 8. Hypotenuse is 17. Boom, sine is done. Cosine is adjacent over the hypotenuse, so 15 over 17. Excellent. Tangent is opposite over adjacent, so 8 over 15. Now for my reciprocals. Cosecant is the reciprocal of sine, so it's hypotenuse over opposite, or just flip this guy, which is 17 over 8. Secant will be the reciprocal of cosine, so we're going to flip that and get 17 over 15, or you can think of it as hypotenuse over adjacent. So 17, over 15. And then lastly, we have cotangent. Well, cotangent is the reciprocal of tangent. So flip the 15 over 8, or you can think of it as adjacent over opposite. So 15 over 8. All 6 done. Without even breaking a sweat. All right, there we go. But it all stems from getting that first missing side there. Otherwise, you can only do sine and cosecant. Then if you don't have that third side, you're only getting 2 out of the 6 points there. That's a third of the points. You don't want that. Okay. Now this one here, got to be careful because it's not actually a triple. If this 5 was the hypotenuse, it'd be a 3, 4, 5 triangle. But this is one of my sides here, or one of my legs here, so I actually do need to use some Pythag to figure this one out to start. So we got 3 squared plus 5 squared equals c squared. That's 9 plus 25 equals c squared. So we get 34 equals c squared. So it's going to be the square root. So c equals the square root of 34. And that actually cannot be broken down, so we'll leave it as such, square root of 34. If I divide that by 2, I get 17, and there's no pairs. So we just have this ugly radical here, square root of 34. All right, let's get these ratios popping here. So for sine, well, actually, let's label this. This is going to be my opposite here. This is my adjacent, once again, and this is my hypotenuse, okay? Now we're ready to rock and roll. Now we're ready. Sine is my opposite over my hypotenuse, so that is 3 over the square root of 34. Now, unfortunately, children, there's this rule in math where we have to rationalize our denominator as a final answer. You're not allowed to leave a final answer like this in the math world. It's just, we're not allowing it because some old dude said that we have to do that way back in the day and we follow this blindly, right? I absolutely hate this rule. I think this is fine, but your teacher likely doesn't. Standardized tests say you can't, so we have to rationalize it. We have to follow what they're telling us. We got to multiply by root 34 over root 34. That's going to give me 3 root 34 over 34. So this is my final answer. Now, you tell me with a straight face that this looks better than that. They both are ugly, right? They're both terrible looking, so why do the extra work? I think this is fine, okay? But apparently we have to rationalize. I'm saying let's start a movement, guys. Let's start a movement. No more rationalizing of denominators. Leave it like that. That's it. We're done. College Board, I need you to hop on because you're the big dog, okay? And then we'll all follow suit, right? So let's make that happen. I'm going to start a little petition online to make that happen, and then we'll change the world. Okay, moving on. For now, I'll just show you how to rationalize. Adjacent over hypotenuse. That's 5 over the square root of 34. And guess what? We get to rationalize again. So same deal. You're probably like, I know what it's going to look like. That's fine. So we multiply by root 34 over root 34. And now I end up with 5 root 34 over 34. So it's kind of like bleeding into the next one there. All right. Tangent. Oh, thank goodness. No radicals in this one, guys. No radicals. It's just going to be opposite over adjacent, so 3 over 5 for the tangent one. Yay! I'll circle that. It was so simple. All right, now cosecant. So cosecant is the reciprocal of sine, right? Now, here's another beef that I have with rationalizing of denominators. If I did the reciprocal of this, I got to rationalize and simplify all over again. So perhaps we just use the original one that wasn't rationalized. It's root 34 over 3. Or we can just think of it as hypotenuse over opposite. Cool? That one's good. Now let's go to secant, and I'll bring the secant one out. We'll use a different color because it's getting a little tight here. So secant is my reciprocal of cosine, or you can think of it as hypotenuse over adjacent. It's root 34 over 5. Okay? And then lastly, after I circle it, lastly is cotangent, which is adjacent over opposite, the reciprocal of tangent, which is going to be 5 over 3. There we go, guys. We got them all 6 trig functions, each situation there. So here it's not too bad, all integers, no rationalizing required. Here we have to rationalize a few times, which again, I don't like. Every once in a while, it works out kind of nice. But with these, this looks like worse than that. I can't get over it, okay? I don't want to rationalize anymore. So hopefully we can start a mathematical revolution here and stop rationalizing denominators. All right, I'm off my soapbox, right? I'm standing on one now. I know I'm pretty short. Anyways, I'll see you guys later.